Okay, gentlemen, welcome back. Sidara, can you hear me? Hello?
Yes, we can hear you.
We can hear, right?
Yes.
Okay, guys, because I cannot see you anything, I think you cannot see me, so if there's anything wrong, let me know, okay? Just stop and tell me. I mean, if there is a kind of echo or you cannot hear me well. Guys, let's continue. So, the first part today is a kind of introduction today. So we'll talk about vectors. As you know, vector is a directed line segment that corresponds to a displacement from one point A to another point B, right? And because when you just say line segment, that is a line segment, all right, but if you just put a direction to this here, with arrowhead we show this, that means that something is moving in this direction, right? And its displacement is from this to this. And this concept is used especially in physics and a lot of force problems. In general, they have some magnitudes, right? They have, I mean, the quantities, they have magnitude and direction. That vector is the best thing to describe such quantities. So if we have line segment, when we say line segment, we know that it has initial point and it has end point. And also it has the length, because when you just say line, it doesn't have end point, it doesn't have initial point. That's why it doesn't have length. But when we talk about the line segment, it has length. That describes the magnitude of that thing. If you're talking about the force, that describes the magnitude, or that represents the magnitude of the force. So anyway, here when we just say vector, as you know, this kind of things comes to our mind, right? The first thing, that is a directed line segment. So here, usually, if I denote the initial point, this is called initial point or tail, let's say capital A. End point or terminal point, let's say with B, okay? Then how do you show that it is a displacement from A to B? Then we just use this notation, A, B, and here we have arrowhead. So there's a displacement here from A to B. And how about if I draw another vector, let's say from here, okay, I can show this, I can label this initial point as B, it's moving from B to A. And let's make another one, B to C, for example. So it is actually the displacement from B to C in this direction, right? How to show this? With capital letters B, C, vector B, C. That is the initial point, and this one is, what is it? Terminal point, or that is tail and head, right? As you see here for vectors, the two important things, right? There are two important things about vectors. Number one is it is length, that's a magnitude, right? And also it is direction, okay? So often also actual vectors are denoted by a single bold-faced letter, right? Like for example, let's say this one is vector A, that one is bold-faced, okay? But sometimes it's hard here to write something because you cannot distinguish between bold-faced and just normal A. And how about this one? Let's say this bold-faced B, okay? So the thing is, this one is vector A. Here we have bold-faced A, and here we have bold-faced B. Okay, but in this course, most of the time, we will use this notation for vectors, bold-faced. And sometimes, just because, as you see here, for me, writing bold-faced is hard, simply I may use this thing. That means a vector A or vector B. All right. So the set of all points in the plane corresponds to the set of all vectors whose tails are at the origin. So when we just say the plane, we know that things, actually, when we talk about geometry, we have three important things, right? Number one is point, second one is line, third one is plane. So that is our plane. Let's say that's our plane. That is our Cartesian plane. And let's say this one is x-axis and this one is y-axis. Now that's our Cartesian plane. How many points we have here? We have infinitely many points, right? And we are saying that every point here, I mean the set of all points here, and also here we have the set of a lot of infinitely many vectors here, right? If we just take one vector from here, for example, let me just change and color. Take one point, actually that point corresponds to this vector. And if you take another point here, for example, this point corresponds to this vector, right? If you take another point here, for example, this point corresponds to this vector. If you take this point here, for example, it corresponds to this vector. And how many points? We have infinite vectors here. See, because here we have infinitely many points, and each point corresponds to one unique vector here. So to each point A, let's say this one is point A, right? There corresponds the vector OA, because we know that when we draw actual Cartesian plane, the intersection point, we call this origin, right? It is denoted by O. So this point is A. So that is from O to A. So that vector is this bold phase actually, that is OA. So each vector with tail at O, that corresponds is head A. Actually, this one is again bold A. Actually, that's a vector. Okay. So vectors of this form are sometimes called position vectors. That means that when we just say position vector, simply we mean that the tail of the vector is at the origin. Okay. So that is called position vector, because vector, we may have another vector here, right? We may have another vector here, but we are saying that if we just locate the tail of the vector at the origin, then it becomes a position vector. Or just when you say the position vector, you should think that the tail of the vector is at the origin. Okay. So since it is in the coordinate system, right, it makes sense actually to describe this vector with coordinates. That means that an ordered pair of numbers. For example, for this point, we know that in the coordinate system, every point is described by a pair of ordered numbers or ordered pair of numbers. Let's say this one is 4 and this number is 2. Okay, so this vector is A. So vector A, actually I can just describe by an ordered pair of numbers. That is 4, not 4. Let's say this one is 3. So that is 4, 3, right? And when you just write like this, we call it, it's a row vector. In different form, also we can just write it as you know, it is 4, 3. But throughout this course, most of the time, we prefer to use this notation. Okay, because why is it so? It's easy to understand. When I just say this, you need to separate by a comma here, right? And this thing is, you will see that it's more practical using this row vector. So that's called a row vector because it has only one row, and we call this one, what is it? Column vector. Okay. And how about these numbers? How we call this? We know that each individual number here, right? And we call them components, because now we are just trying to get familiar with the terminology, so we are going to use them often. Components. So how many components does this vector have? It has only 2. Why? Because it is in 2-dimensional space. If I have 3, for example, at the time it will have 3 components. 3 components means the vector belongs to the 3-dimensional space, right? If it has 4 components, then it belongs to 4-dimensional space. So why we say actually geometry of vectors, actually drawing here, introducing this coordinate system, right? That's involving geometry here. That's why we call here the geometry of vectors here. How about algebra? Algebra means using these variables, right, with these components. That is the algebra of vectors. And also now we will see how to add and what is the subtract vectors. First, let's see this example. Example 1.1, vectors in the plane. If vector A is -1 and 2, B is 3, 4, find AB and redraw it. Okay, what are these? As you see here, it's not square brackets, right? They are not in square brackets. That means that they represent a point, right? So if you draw this in standard position and with its tail at the point C minus 2. Well, so we have two questions here. Question A, here, if you just draw this immediately, finally, okay. First, let me just find this vector. So let's say that's minus 1, 2, minus 1 is somewhere, 3, 4. So that is our vector. This point is A, whose coordinates are negative 1, 2. And this point is B, whose coordinates are 3, 4. Okay. So how do you find this vector, for example, AB? The question is, we need to find AB, right, in standard position. How do you find this? If this one is our origin, let's say, so if you just form new vectors here, that one is OA, and here, this one is OB, right? And we know that it's a displacement moving from this point to this point and from A to B is the same as moving from A to O to B. It is the triangular addition, the triangular addition of two vectors. That means that here, what is AB? AB is equal to OA, right, from O to A and plus O to B, plus AB, sorry, from here, OB equals OA plus AB. So from here, we need to find OAB. What is AB? Then AB is equal to OB minus OA. Right? So from here, that's equal to, let me just write as a column vector. What is OB? OB is this, right? Coordinates are 3, 4. It's a position vector because tail is at the origin. So that is 3, 4. Minus, how about OA? OA is minus 1, 2. So if you subtract here, we will get this. 3 minus minus 1, that is 4. 4 minus 2, that is 2. So that is our vector AB. What is it in standard position? Right, in standard position, that is 4, 2. If you just draw this vector, it will have, AB will have, okay, already drawn here. We don't have to draw it here. That is AB in standard position. Okay. And so that is here. I can maybe this here. That's our, let's say, y-axis. This one is x-axis. So that's AB. We know that for the vectors, location is not important, right? What's important is its length and direction. So in standard position, this AB, I can draw here. Exactly the same vector here. That is A, and this one is B, or OB. Okay, what is it? It is 4 and 2. This one is 4, and this one is 2. And how about question B? And question B, with its tail at the point C minus 1. Okay, with its tail at the point C minus 1. How do you do that? Here, draw this. Okay, my drawing is a bit X and Y. 2 minus 1. Where's 2 minus 1? Okay. Here we have 1, 2, and negative 1. This one is negative 1. So 2, 1 is here. This is the point C, right? It says that with its tail at the point C equals 2 minus 1. So the tail of AB must be here. And what are its coordinates? 4, 2. It is 4 to Y. It is It is 2. 4, 2 means, so 4 units to the right and 2 units up, right? 4 units and 2 units up, it will be somewhere here. So this will be our vector A. So that one is A, B. Standard position, it is here, right? A, B. And originally it was here, right? That is A, B. Okay. Describing the same vector in 3 different ways. Standard position and placing its tail at the given point, that is C. Coordinates C are 2, -1. Good. Another example is about new vectors from old, the addition of vectors. It says that we are given vector u, whose components are 3, -1, and v, 1 and 4. Compute and draw u plus v. Okay. Component-wise, how do you add them? We just add their corresponding components. So that is a here. If you add, let's say, u plus v, and these are vectors, and the components of u, it is 3, -1, is given as row vector, 1 and 4. So if you add your corresponding components, 3 plus 1, it is 4, right? -1 plus 4, that is 3. That's the resulting vector. And draw u plus v. How do you draw u plus v? It is 4, 3. Here we have Cartesian plane, y-axis and x-axis, 4, 3. Here we have 4, and here we have 3. So the vector will be this vector. So that is vector, what is it? U plus v. Okay, and I can draw here 3 minus 1. 3 minus 1 is somewhere here, right? And another that is u. And how about v? 1, 4. 1, 4 is somewhere here. So their addition is this vector u plus v. And how about b? If v equals, the components of v, vector v are -2 and 4, right? Compute and draw these things. So v, components of v, it is -2 and 4. Number 1, 2v. 2v. What is it? It is 2 times -2, 4. Actually, multiplying a vector by a constant means it's just either extending, right, or shrinking. That is, multiply each component by this. It's like scaling a vector 2 times -2, that is -4. 2 times 4, that's equal to 8. And the second one, 1 over 2v. Here we have 1 over 2, -2 and 4, which is equal to -1 and 2. 3, -2v, since we are multiplying by a negative number, as you know, also change the direction, right? The opposite side. So here we have -2, -2, 4, which is equal to 4 and -8. So it says compute. We have already computed. Here in the second part, it says draw. How do you draw this? Let's use green here. Oh, it's blue. X, Y, right? -2, 4. -2, 4, where is it? -2, 4, it is somewhere here. That is our original vector. This one is -2. This one is 4. The first one, 2v. What is it? -4, 8. So -4 and 8, it will be just somewhere here. This one is, what is it? 2v, this vector. right? And half v will be, it is minus 1, 2. Minus 1, 2 is this vector. That is half v. And minus 2v, it means the opposite direction. That is 2 times longer than this vector. So it will be this vector. That is negative 2v. Okay. Guys, any question? These are very easy, basic concepts. Another one is example 1.3. It says that let A, B, and X denote vectors in Rm. Okay. So now what we say by Rm, that means that again, it's just a vector, but which has, or is described by n components, right? So that means that if you just take any vector, let's say like vector A is from Rm. What does it mean? It means that this A has n components, right? The first component is x sub 1, x sub 2, dot, dot, dot. Here we have xn. How about if B is, for example, it is from R3. That means that B is something like this. It has B1, B2, and B3. So in general, the addition and the component-wise subtraction is the same. That's why it doesn't matter here. It's from n-dimensional space, 2-dimensional space, 3-dimensional space. You know, vectors, simplify. A. So here we have 3a plus 5b minus 2a plus 2 times b minus a. These are vectors. It's very similar to real number algebra, right? So here we have 3a plus 5b. First remove the brackets, minus 2a plus 2 times b, this 2b minus 2a, which is equal to, let's simplify a's first, 3a minus 2a. It is 1a, 1a plus minus 2a. Here we have minus vector a. And 5b plus 7 is 2b. That is 7b. Right? Not all properties are the same, but this addition subtraction is exactly the same with real numbers. How about b? It says that if 5x minus a equals 2 times a plus 2x, solve for x in terms of a. So here we have 5x is a vector minus a equals 2a plus 4x, right? And take to the left-hand side, 5x minus 4x, that is x, that's equal to 3a. So we have expressed the solution x in terms of a. Algebraic properties of vectors in Rn. Okay, so again, in Rn, once again, what we mean here is this U, V, E, W, R from Rn means each vector is described by n components, right? So for example, if it is 3, let's say you'll have 3 components. If it is 4, we have 4 components. In general, if it is m, once again, it is something like this. Here we have U, right? It has n components, U sub 1, U sub 2, dot, dot, dot. Here we have U sub n. And how about V? Also, it has n components, V sub 1, V sub 2, dot, 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 V sub n. And also W, the same thing. Here we have W1, the first component, and second component, and it has n components. So it seems that they are easy, but they are really important. Throughout this course, we are going to use these properties a lot. It says that let C and D be scalars. D and B are scalars, means these things are just our real numbers, right? Then it says that commutative over addition, that is U plus V equals V plus U, right? How do you prove that? Actually, if you just write here u plus v, what is u plus v? I mean, you can just put other stuff like in similar way. Is component wise. Number one is u plus v. By the definition, it is this, right? What is vector u? It is u1, u2, dot, 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 un. Plus, how about v? V is v1, v2, dot, dot, dot. Here we have vn. Now, what is the definition of addition? Just to add two vectors, we need to add their corresponding components. So here we will have u1 plus v1, u2 plus v2, dot, dot, dot. Here we have un plus vn, which is equal to, by using the property of real numbers now, I can write it as v1 plus u1, because this v's, these are real numbers, right? A plus b equals b plus a. So here we have v2 plus u2, dot, 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 vn plus un. And again, using the definition, we can write it as v1, v2 plus vn, right? Plus, and here we have u1, u2, un. Very easy. And just students, they don't understand what they have to do. That's why they feel actually linear algebra, it is very easy course. And similar way, you can prove this. U plus v plus w is associative property equals u plus v plus w. And in this space, we are talking about a space, right? A kind of space here that is n-dimensional space. And we have a lot of vectors here. Some of them, let's say it's u, v, w. We have infinitely many vectors here. And also here we have one special vector. We call this zero vector. As see, it's boldface 0. So zero vector means whose all components are 0. It says that if you just add this zero vector to any vector, the resulting vector will be again itself, that u. Okay, 5 minutes left. And if you multiply, and also here we have, for every vector, we have another vector that is denoted by minus u. If you add these two vectors, it will be zero vector. And u plus v, if you just add two vectors and multiply by scalar c, it is the same as first scale this u and scale this v and add them up. Okay, it's the same thing. And c plus d, these are two real numbers, right? E times u equals c times u plus d times u. And it's a similar thing. And also here, 1 times u equals u. Okay, maybe later we will see that this one is, we call this identity elements, okay? Now, in this vector, it's just our usual one. But this identity element is may not be usual one always. We will see them later. Okay, for here, just one. So we have some identity element 1. It's 1. If you multiply every vector by 1, that's equal to u. Actually, here we have this real number 1, scalar 1. Good. Guys, we have one thing left. Okay, after that, I will finish the class for today. And we have another concept that we are going to use a lot in this chapter, in this course, that is linear combinations and the coordinates. This linear combination we use a lot. That must be like a piece of cake for everybody. When it's a linear combination, immediately you have to be able to visualize this thing. Think of this thing, okay? So, what do we mean by a vector V is a linear combination of vectors V1, V2, Vk. Okay. It means that if there are scalars C1, C2, and Ck, such that V can be written as C1 times V1 plus C2 times V2 plus Ck times Vk, then we say that V is a linear combination of these vectors, V1, V2, and Vk. So the scalars C1, C2, and Ck, they are called the coefficients of the linear combination. Okay, it's very simple concept, simple definition, but you will see that since it's a linear algebra, we are going to use this a lot. Let's just see one example. Assume that we are given vector V, whose components are 2, -2, 1. Vector A, whose components are 1, 0, negative 1, B, 2, negative 3, 1, C, 5, negative 4, 0. As you see here, it has 3 components. That means that all these vectors are from 3-dimensional space, right? Now, the question is, if I ask you without looking at closing this part, is W a linear combination of A, B, C? Or in general, is any of these vectors, W, A, B, or C, is a linear combination of the remaining vectors? That's a big question. Now we are going to answer this question later, okay, because it's not that we cannot answer in a very short time. We have to go through a lot of calculation. That's a big task. So here, assume that we know the technique how to find this, and we answer the question. And the answer is yes. That means that W equals 3 times A plus 2 times B minus C. We are finding this. Here C1 equals 3, C2 equals 2, and 3 equals negative 1. Finding this number is not that easy. Okay. Anyway, assume that we know how to find this. We found this, and now we are showing that. As you see here, 2, negative 2 plus 1. Multiply the first vector by 3, the second vector by 2, the third vector by negative 1. Add them up, and we will get this vector. 3 times 1, 3, 2 times 2, 4. It is 7, 7 minus 5, 2. In a similar way, you can check other components. This will be true. It's just one example to understand what we mean by saying that given vector is a linear combination of, let's say, k vectors or n vectors. Okay, we mean this. It is possible to write vector v as a linear combination of a, b, c. It may not be possible, right? It may not be possible. For example, if I ask you, okay, the last example, vector A, whose components are 1 and 2. Vector B is, let's say, 3, 5. If I ask you, is A a linear combination of B? Here we have only 2 vectors, right? So that means that can you just write A as K times B? Can you find such number? We cannot, right? Because if you multiply any number, you will see that here we will have A is equal to 1, 2. If you multiply B by K, here we will have 3K, here we will have 5K. From here, if you find this, what is K? From the first part, K equals 1 over 3. From the second one, K equals 2 over 5. We know that K, just one number, it cannot be equal to 2 numbers at the same time. So that means that BA cannot be a linear combination of B. Now I cannot have one more vector. I cannot have more vectors. And the problem gets a bit more complicated. But here, we are just trying to understand what we mean by linear combination. Okay. Gentlemen, that much is enough for today. Thank you very much. As I told you, I record the lesson and put everything in the folder. Okay, share you the link. If I upload this in the YouTube, I can do this later, but it's taking a lot of time. For now, I'll just share the link, put all the videos in my Google Drive, okay? You can reach through the link. Thank you very much. See you tomorrow at around 10 o'clock. Bye-bye.
Right, sir.
Bye-bye.